Hello dear viewers and welcome to this video lecture. So in this video lecture we are going to learn RASA algorithm. So RSA algorithm is based on asymmetric key cryptography. So very basic, we already did the symmetric key cryptography. Symmetric key. In a symmetric key, here is a sender and here is a receiver. So sender is going to send a message and that message is going to be encrypted with the key, or you can say encrypt the message with some key. Now the receiver will receive this message and going to decrypt with the same key K. Let's suppose that K is our key. But here the receiver will apply that key in a reverse order. The main challenge in this symmetric key cryptography is the sharing of a key. So we are going to use some secure channel to share the key separately. So that was the symmetric key cryptography. There are several algorithms, substitution ciphers and transposition ciphers, in which the sender is going to share a key first with the receiver, then it's going to send a message in an encrypted form using the same key. So this is a symmetric key cryptography, or it's also known as one key cryptography. Okay, so now whereas this RSA algorithm is based on public key cryptography. This is also known as asymmetric key cryptography. Asymmetric key cryptography, or it's also known as two-key cryptography. Okay, now let's have a basic of this, that how this asymmetric key cryptography works. Here we are having a sender and here is a receiver. Let's give these characters a name. This is the Alice and this is a Bob. So now here in asymmetric key cryptography we are having a pair of keys. One is known as a private key, so this is a private key of Alice is having a public key, and these two keys are formed in a group. So what I mean that if a message is going to be encrypted with this private key, that is going to decrypt with this public key, and vice versa is also true. If you are going to encrypt this message, the public key, that is going to be decrypted with a private key of A. So this is the basic principle of asymmetric key cryptography. So now here in this particular scenario we are having two users, Alice and Bob. Alice is having its own set of key and Bob is also having a own set of key, that is a private and a public. So now let's suppose Alice is want to send a message M to the Bob. Now Alice is having four options over here to encrypt this message. Either it's going to encrypt with this private key, but if he is going to encrypt this message with A private, what will happen in that particular case? So A public. Okay, so basically I have given you the information that these two are the pairs. If you are encrypted with the one key, that message is going to decrypt with the another key. So now basically this private key generally hold by the owner only. No one else have access to that private key. Whereas a public key, that is shared on a public domain. Let's suppose here in this network we are having the some other users also which are present over here. Okay, so now A is going to encrypt. Let's suppose A is going to encrypt this message A private. So now A public is available in this domain. It means A private, this message can be decrypted with the A public, and A public is available to all of the users in that network. So there is no use of using or encrypting a message with the A private key, because everyone else have a public key to decrypt that. So this first option is not feasible. Now let's take a second scenario, that is A public. So now let's suppose Alice is going to use a public key to decrypt that, but now the condition holds that this private key is only owned by the Alice. It means no one on a network, not even a Bob, can decrypt that message. So this option is also not feasible one. Now we are having a among these four options, two we have discarded. Now the third option is that we can encrypt this message with B's private key. But now this is a private key and that is access to only Bob, whereas this is a publicly available key of a Bob. So A can't access to the B private, so that is not even accessible. So we are left with the last option, that is B public. So here B public is only feasible option in this scenario. So now let's see that how this is going to be executed. Now A is going to encrypt this message with B public, that is going to be encrypted. This message is now encrypted form. Now this message is sent over to the network over here, that is in an encrypted form, or you can write this as a M dash. Now that is encrypted. Now that is sent over this network. Let's have this user Eve. He also want to tag this, but this message is in an encrypted form, and Eve have access to the public keys A public, B public, and its own public. Now this message can only be decrypted with now B private, because it is encrypted with the B public. It means only Bob can decrypt this message with the B's private key. So this was the basic of public key cryptography. So now let's have a look at the RSA algorithm, that is basically based on only this algorithm. So now let's consider the same scenario. Alice and Bob, two user. Now Alice want to send a message, let's say 2. Alice want to send 2 to the Bob. Now first it's going to encrypt this with the public key of Bob. Now first we have to compute private and public key for the Bob. So the steps are, well, first step is that Bob is going to choose 2 random very large private numbers. Let's say P and Q. P and Q. So these 2 are prime numbers. P and Q are prime numbers. Prime numbers, and that are very large. Basically, what are the largest possible prime numbers we are going to choose among those which can fit into a computer memory. Okay, so now the next step is, same step is, we are going to compute n, and that is equal to P into Q. Okay, so now we are also going to find phi n in the first step, and that is P minus 1 into q minus 1. So this is our first step, taking the two private keys and finding the n, which is the multiplication of two prime numbers, and then we are going to find the phi n, that is p minus 1 into q minus 1. Now next step is to find e. We are going to find e with condition such that e would be equal to and greater to 1, and that would be less than phi of n, and your e, GCD means HCF, GCD of e and phi of n, that is equal to 1, means e and phi n should be co-prime. Co-prime means there is no common factor, only one is a common factor of e and phi. Now the third step is to find the d. Find the d. We are going to find the d. So now d would be e inverse mod phi of n. So now that is a d. So now up to here we are having these values, that is n and e and d. So now we are going to share e and n, and that is a combination. E and n is a combination of a public key. So that value, this value would be the public key of B. So B public. We are here to find the B public now. So B public would be E and N. Whereas private key would be N and D. So this would be our private. We can write B private, that is N and D. So this combination would act as a private key of a Bob. So now we are going to encrypt this M with this Bob's public key. So now we are going to find the ciphertext or encrypted text that is congruent to M raised to power E mod N. So we will have one value, and here we already have some, I already uploaded some videos regarding modular arithmetics. So here you will get one value by solving this, and after that the Bob, now Bob has encrypted his message with this Bob's public key. Now message is encrypted and sent to the Bob or sent to the network. So now in a network, Bob is having this C. Now Bob is going to extract a plain message, and that plain message, that is equal to C raised to power D mod N. So this is how our algorithm works. Okay, so that is congruent to this one. So in the next video lecture, we are going to put some values and see that how mathematically this model or this algorithm will work. Okay, thanks for watching, and subscribe to my YouTube channel if you find this video useful. Stay safe. Thank you.